Hi everyone, I'm Isabel. First of all, I'd like to thank the organizers for the conference and for financial support. I'm in a postdoc position from Argentina, and I will talking about X-ray and TESS data for some symbiotic studies. Symbiotic studies are a kind of CVs causing in a huge scales. I mean, they are compact binary systems, but instead of main sequence star, we have a red giant as a secondary. The white dwarf is the primary, but in a few cases we can have a neutron stars. So, differently from CVs, symbiotic stars have a nebula around the systems, which is ionized. And the combination of the emission from this nebula and the absorption emission from the surface of the red giant in an optical spectra is the reason for symbiotic stars called symbiotic stars. In terms of X-ray classification, X-ray emission, symbiotic stars can be classified as alpha, beta, gamma, delta, and beta-delta type. So alpha type are super soft sources, and the X-ray emission comes from the quasi-stellar thermonuclear burning on the surface of the white dwarf. Beta type soft sources, which the X-ray emission comes from the coolant wind for the red giant and the white dwarf as well. And the gamma type are neutron symbiotic stars, and they emit in the red energy. Delta type are hard sources which the X-ray emission arise from the accretion from the boundary layer. And finally, beta and delta type have two components, in one from the soft energy, which X-ray comes from the coolant wind, and another one with in hard component, which X-ray emission comes from the boundary layer. The material from the red giants can be transferred via wind by capture, Roche lobe overflow, similar to CV, or wide Roche lobe overflow, with stellar wide fills the Roche lobe. In comparison with other white dwarfs accretors, symbiotic stars have the longest orbital period, the higher accretion rate, and can have flickering or not. Oh gosh, sorry. Actually, UV flickering is common in symbiotic stars and have correlation with hard X-ray emission. In this figure, shows the relation with the fraction UV flickering, the fraction UV flickering versus hardness. And as you can see here, more hard X-ray emission is, more intense the UV flickering. And flickering is an important diagnostic of the accretion. Well, at the moment I'm working with these four symbiotic stars. I'm using Swift, XMM-Newton, and TESS data as well. And NQGen is the only one with previous. It was the only one with previous results using Swift data. So for that reason, now I'm using only XMM-Newton data. In relation with our X-ray data, we figured out that Swift, XRT, and PC mode data for BDCAM and V1261 Ori have optical loading, and they cannot be used. So optical load produce a spurious signal in a CCD due to the bright sources. So it doesn't depend on the exposure time of the source, but the reading time of the CCD. And generally, they affect the energy below 0.4 Kelvin, but the hard energy can have the contamination as well. So here, in this spectrum, this emission in low energy are not real. And the hard energy have the contamination as well. And so, just to let you know, BDCAN has 5 meg, and V12 has 8 meg, both in V-band. Okay. Here is the true spectrum of the BDCAN, observed as a target of opportunity from Swift in WT mode, which runs 1,000 times shorter than PC mode. So for this spectrum, I only use a simple model with absorption and a thermal for just only one component. It means in a soft energy. While for NQGen, I'm using 2 models, the same with absorption plus a pack for 2 components. Soft one and another for the hard one. Well, I'm using Bayesian analysis, X-ray analysis, BXA, but I won't show you here, and I'm not neither the other results, but in general, the spectra can be fitted using observed optically thermal models with single or multi-temperature. And the spectra are all compatible with the X-ray emission comes from the boundary layer. And in terms of the sense, I improved the sense of the X-ray emission classification. BDCAM, it's a beta. V12 and CD27, it's a delta, and NQGen is a delta-delta type, which was previously reported. Well, in order to look for the flickering in optical emission, we also analyzed the data from the OM, XMM, and for TESS as well. So here for NQGen, we found a flickering with a few amplitudes. And just for curiosity, NQGen doesn't have a SAPE or PDC SAPE light curve from the MAST website, so I needed to use FFE image for this object, and also I analyzed the others with the same way. So next, I looked as well for the periodicity in this data, in the optical data, and just for NQGen here, that I'm present, I'm using the next figure this part of the TESS data. It's the 44th section of the TESS, and we applied the red fit code, which estimates the red noise. And as you can see here, the red is the signal of the red noise, and the green is the for my data, and unfortunately the head noise is higher than my source, so we didn't find periodicity yet. Well, I mean, in summary, for the optical emission, none of my objects have periodicity. And, but they have some stochastic variability, I mean flickering. And this optical flickering, well, it's a good diagnostic of accretion. And my sources are powered accretion. Well, my conclusion so far, well, I'm present now. I'm present for symbiotic stars, and I'm improve the X-ray census of the classification. Also, the hard X-ray emission and flickering indicate my sources are accretion-powered, and unfortunately, no periodicity was found. And finally, be careful. If your target is bright and you are using Swift in PC mode, your data can have the optical loading. Yep, so that's it.
All right, thank you very much.